All right, Jacob, we're going to talk about two things and hopefully we'll clarify a little bit of what's going on. So the first bit that I want to talk about is what we talked about, this K, which is our wave number. And to understand that, I want to look at the way that we described our light. We said it was e to the ikx minus I omega t. And this just sort of described our light that was moving like this. Light's a wave, so it looks like that. And the sort of moving part, right, and we talked about, let me see if I can get this. So this is sort of the moving part. And in the discussion of the interferometer, we actually said we don't need to mess with that at all because the interferometer doesn't change anything about the moving part, okay? But what the moving part does have is it has this omega, right? And the omega is what we call the temporal frequency. And we're going to talk about K in just a second, but it's basically the same thing as omega, temporal frequency, which is an idea of like waves per time. So like how many waves pass by a given location in space in an amount of time. So the idea is like, are there a bunch of peaks that move rapidly, or are there a bunch of peaks that the sort of like frozen in time spot, is it sort of going slowly? So omega is a temporal frequency, and none of the mirrors in the Fabry Perot interferometer mess with temporal frequency, which is why we can just sort of ignore it. And we'll actually get into some details of that in a second. But this ikx, we have K, which is the wave number. And K is actually specifically 1 over the wavelength. And the wavelength is, of course, like this distance here. This is the wavelength. It's the length per wave, right? So it's like, hey, so like a wavelength would be like 2 nanometers, right? So if you had a wavelength of 2 nanometers, basically what that tells you is it's 2 nanometers per 1 wave, right? Which means the wave number is the inverse of that. You actually just flip the fraction. So that gives me K is 1 wave per 2 nanometers, right? So if you have a wavelength of 2, you have a wave number of 1/2. They sort of flip each other. And the idea is that like wavelength gives you like the length of a wave, but wave number gives you waves per length. So, and that length can be whatever you want it to be. It's sort of like, you know, you could measure distance in meters or yards or feet. You can have wave number in sort of like waves per nanometer, waves per picometer, whatever, based on sort of like the light that you're doing. So that's what wave number is. And we are going to talk about that in a very specific way. Okay, so let's go to our actual interferometer and see how all of this stuff kind of carries out. I'm going to move it up a little bit on the page so that it's a little bit more compact. So here are both of our mirrors, and they are d length apart, right? The length between them is d. And just for like notational sake, I have one at x equals 0 and one at x equals negative d. I could have this one at 0 and that one at d. It doesn't really matter. And what we want to keep track of is the light as it moves through our apparatus. So the initial bit of light, I could draw these as waves, but I don't really want to because it's going to be hard and it may end up looking not exactly what we want. So I'm going to say we have light that comes through A0 e to the I kx minus omega t, omega I omega t. Right, and this is our moving light. Okay, so what we know about our light is that nothing in our apparatus actually changes anything about this part, right? The mirrors are just set up. They don't change the temporal frequency of your light wave at all. So what we can actually do is, instead of writing it like this and keeping track of all the I omega t's, this, you can really think of this because of sort of exponent properties. I'm going to go like right here. I'm just going to kind of squeeze it in up here. This is really like A0 e to the I k x divided by e to the I omega t, right? Because it's a negative exponent, and if you multiply things with a like base, you just add them. And really, this is then, I can think of this as a new constant, a, which sort of wraps in all of the old stuff that doesn't change, e to the I omega t. And because this e to the I omega t doesn't change, now I can rewrite this as a to the e to the I k x. And now my a is not going to change at all, and it's just a little bit easier to write all of this stuff. Because of the way the interferometer is set up, I know that this time stuff is not going to change. All right, so when the light hits the first part of the interferometer, some of it bounces back. Okay, so this is the sort of reflected. And then this is the transmitted. Okay, and here's the important thing to know. This is sort of the way that the whole piece works. Reflected light picks up a phase shift. Transmitted light is not phase shifted. This is just like a general rule of optics, and this is sort of the idea that we're going to take advantage of throughout. So this first beam of light is actually not phase shifted at all, but because some of it bounced off, this is a little bit dimmer, right? So whatever the transmissivity coefficient is, right? Like we said, a certain percent of the light, T, say, could be like 0.9, indicates that 90% of light goes through. Which means that this light is now a t, maybe 90% of it, maybe 80% of it, e to the I k x, right? So in the middle of the interferometer, it's a times t because it's a little bit dimmed. It's dimmed by a factor of t, and then e to the I k x. This part has not changed at all because this blue light has only been transmitted. The part that's reflected, this stuff here, picked up a phase shift, but we don't care about that because that's not going to hit the detector. And then what happens? It goes through the next partially reflecting mirror. So this is now a t squared e to the I k x because it got transmitted twice. It got dimmed here at the first mirror by t. It got dimmed here at the second mirror by t. So that's the first bit to go through. And I think in the book he calls that U0. U0. It's just the sort of first piece of light. Unbounced light. Okay. And then, but because this mirror partially reflects, some of it gets bounced back. And this is the important part. This red light, when it's going this way, it's a t, right? Because it only got transmitted once. It only transmitted here. But it also has a reflected bit, right? So like some of it got it gets dimmed because it's reflected, right? So if 90% of the light went through, only 10% of the light went back. So the dimming factor is now T times R, and it picked up a phase shift. We'll talk about the phase shift in just a second. ATR e to the IKX. And remember, we said a phase shift is like cosine, like kx plus theta. Now, calculating phase shifts is really, really difficult if you're in this sort of formula. But a phase shift, if you think of it in e to the ikx terms, a phase shift is just some additional e thing. And it turns out the phase shift that it picks up is e to the ikd, where d is the distance between the two semi-reflecting mirrors. This light is actually not that interesting because it's not going to hit our detector. It's going to get bounced again. So we're going to track it for one more bounce, and hopefully we'll see the pattern. It's black now. The light now bounces back. So this light, some of it's going to go through, right? Some of it's going to get transmitted. That's not interesting to us because it's not going to hit the detector. But this light here, okay, has now been reflected twice. So it's A, T, just transmitted once. It only transmitted the first time it went through. R squared, e to the ikx. But because it got bounced twice, it picks up this dimming reflected 2 times. But it also gets phase shifted twice, e to the 2ikd. And now let's think about what happens to this light as it goes through this goes through the last detector. It's going to come out. Okay? Now, it got transmitted twice. It got reflected twice. So now it's going to have A, which is its original sort of brightness or amplitude. It got transmitted here and initially when it came through here. So that's now got a transmitted factor of squared. It got bounced twice, so it has an R squared. It picked up a phase shift of e to the 2ikd because it got bounced twice. It didn't pick up a phase shift on the last transmit because transmitted light is not phase shifted. And now this is the original sort of form, e to the ikx. And this is what's really neat. So now we have our first sort of like, this light here is our like one-time bounced light. This light, so this is the first, geez, I can't write it like that. I'm going to write in a yellow pen, maybe. Yeah. So this is one time bounced. Or this is none time bounced. 0 bounces. Okay. But what I have here, oh geez. This light here, this is 2 bounces. The next sort of light to go through this next sort of beam of light is going to be 4 bounced. So it's still going to be transmitted twice because it went through here the first time and then here the last time. Every bit of light out here that hits our detector is going to only be transmitted twice. But now it's going to have been reflected 4 times. So it's going to pick up this R to the 4th dimming coefficient. And it's going to pick up a phase shift of e to the 4ikd, e to the ikx. And now if we look at our light, I know the video is getting long, but we're like right there. Now all of the light that comes out, right, which we'll just look at it, is going to be an infinite sum. Or well, let's just look at the sum, because light is a sum of all of the component waves. So the first part is a t squared e to the ikx, plus the 2 bounced one is a t squared r squared, so it's dimmed by r squared and it's phase shifted to ikd e to the ikx. And then the 4 bounce one is a t squared r to the 4th e to the 4ikd e to the ikx. And then we'll have some 6 bounced one and 8 bounced one. Everybody here has got an AT squared. So I can just factor that part out. And it's actually, everything's got an ikx on it too. So I'm going to factor out an a t e to the ikx, because that's all in common. And then what I have is, actually, let me do, no, that's okay, times, now this is going to be 1 that captures this first term, plus r squared e to the 2ikd plus r to the 4th e to the 4ikd plus, this one will be my 6 times bounce light, e to the 6ikd plus dot dot dot. And this part becomes my geometric series. Right? And so he's got this part where he's, and the geometric series, the looks like this because it's an infinite number. So I'm going to say I want to do n, sorry. I know, we're going to get there. N equals 0 to infinity. Okay, the part that changes. So AT is not really interesting to me, so that holds on. T, and then e to the ikx, that part didn't change. But now here I have this infinite, and what happens is it's r squared e to the 2ikd to the n, right? So n starts at 0, that gives me this first term. When n is 1, I get this term. When n is 2, I get that term. When n is 3, I get that term. And this is a geometric series, which is 1 over 1 minus r. 1 over 1 minus r squared e to the r squared e to the 2ikd, which gives you this transmissivity that we're talking about. So this is the sort of part that gives me that geometric series. Great. Hopefully this makes some sense. It cleared up maybe some wave number and how everything works. Let me know if you have more questions. I'm definitely ready to help you if you got anything else. All right, see ya.